Hey everyone! Today, we're stepping into one of the most intriguing developments in the unfolding story of the interstellar comet 3I Atlas, a discovery that has left astronomers genuinely stunned. Over the last several months, this object has repeatedly challenged expectations and reshaped discussions about how cometary physics truly works. But the latest observation adds a layer of mystery unlike anything seen so far, forcing scientists to reconsider ideas once thought settled. A new high-resolution image, captured recently in Thailand, has revealed something completely unexpected at this stage of the comet's journey. A sharp, structured antitail pointing almost directly toward the sun, appearing simultaneously with two separate outward-facing tails. Three distinct tail structures, all present at the same time, forming an unusually organized and highly symmetrical configuration. For experienced comet observers, this image was shocking. At this point in Atlas's orbit, any natural antitail should have already weakened, dispersed, or dissolved into a broader diffuse shape. Instead, what we're seeing is the opposite, an antitail that is clean, narrow, finely outlined, and more defined than ever. And beside it, two outward extending tails, each with its own structure, texture, and apparent composition. This isn't what a typical comet should look like. This isn't what conventional models predict. The discovery has ignited a new wave of debate in the scientific community. The configuration captured from Thailand is so unusual, so precisely structured, that it has reopened questions scientists believed were already answered about how comet tails form, evolve, and decay over time. Something about 3I Atlas is different, so different that researchers are now wondering whether they're witnessing a phenomenon that demands a new level of explanation. And that's where our investigation begins. To understand why this new observation is so surprising, we first need to step back and review the fundamentals of cometary tail dynamics. Under normal circumstances, a comet produces one or two primary tails, formed through well-understood physical processes driven by sunlight and the solar wind. The first is the ion tail, a thin, straight stream of electrically charged particles stripped from the comet by solar radiation and carried outward by the solar wind. This tail always points directly away from the sun and typically appears bluish due to ionized gases like carbon monoxide and molecular nitrogen. The second is the dust tail, created when small dust grains are pushed away by the pressure of sunlight. These particles move along curved trajectories, gradually spreading into a wide, smooth, fan-like structure. Dust tails evolve predictably, becoming more diffuse over time as particles disperse into space. Then there is the rare and fascinating phenomenon known as the antitail, the structure now at the center of scientific attention. Despite its appearance, an antitail is not an actual physical tail pointing toward the sunday. Instead, it's an optical effect, produced when large particles, sometimes as big as pebbles or gravel, remain close to the comet's orbital plane. When Earth crosses that plane at just the right angle, the geometry creates the illusion of a tail extending backward, seemingly toward the sunday. In a typical comet, this effect is short-lived. It appears briefly, sharpens for a short window, then fades as particles naturally disperse under gravitational forces and solar radiation pressure. But with 3I Atlas, that expected behavior isn't happening. Instead of weakening after perihelion, where solar heating reaches its peak, the antitail is becoming sharper, stronger, and more persistent. And that's the evidence scientists cannot ignore. So the question now becomes unavoidable. What could possibly be creating such a sharply defined and persistent antitail at this stage in 3I Atlas's orbit? To address this puzzle, scientists are currently evaluating three main hypotheses, each attempting to explain what we're observing and each raising new questions of its own. Hypothesis 1: massive dust grains, released in unusually large quantities. The first explanation is that extremely large dust particles, possibly millimeter-sized or larger, are being expelled from the nucleus. Because they are so heavy, solar radiation pressure cannot push them away quickly. Instead, they remain tightly aligned along the comet's orbital plane, producing the illusion of a narrow, backward-pointing tail. This hypothesis could account for the antitail's sharpness, but it comes with a serious problem. The volume of material required to maintain such a stable and highly defined structure at this late stage would be enormous, far greater than what is typically observed in natural comet outgassing. Most comets simply don't have enough mass or sustained internal pressure to generate such a stream over time. Hypothesis 2. Large icy fragments, acting like mini-comets. The second possibility is that large icy chunks are breaking away from the nucleus and reflecting sunlight strongly before solar forces accelerate them outward. These fragments could behave almost like temporary micronuclei, each producing a short-lived reflective structure before dispersing. While this might explain the initial clarity of the antitail, it does not explain why it remains sharp long after perihelion, the point where solar heating is strongest, and fragmentation is typically chaotic and short-lived. Persistence at this level is not common in the historical record of comet observations. Hypothesis 3. Directed, stable jet activity. The third explanation is the most complex and the most intriguing. It suggests that the structures could be shaped by stable, directional jets emerging from a fixed region within the nucleus. Rather than random explosive venting, these jets would behave like focused channels, delivering material in a controlled and consistent stream. This scenario would require internal fractures, cavities, or structural geometry within the nucleus that organize outflow, producing a configuration much closer to stabilized exhaust than chaotic natural degassing. Experienced observers have noted that the symmetry and persistence of the antitail, combined with the two outward-facing tails, resemble a controlled system, not a disorderly release of dust and gas. To be clear, this does not imply an artificial origin, but it does force scientists to ask whether unknown or poorly understood natural processes could be shaping the comet in ways that current models do not predict. A pattern, too coherent to ignore. This new development cannot be viewed in isolation. 3. iAtlas has already displayed multiple anomalies, including a sun-facing jet, highly unusual in comet activity, locked jets that didn't rotate with the nucleus, non-gravitational acceleration measurable over time, a remarkably stable nucleus that survived perihelion with minimal fragmentation, an ion tail that remained active long after solar heating should have decreased est. Any one of these could be explained on its own, but together they form a pattern that suggests something about 3I Atlas is fundamentally different. And now, with the Thailand image revealing a three-tail configuration active simultaneously, the mystery has escalated sharply. Scientists are no longer asking whether something unusual is happening. They are asking how far from ordinary cometary physics this object may actually be. At this stage, it's important to step back and examine the full picture, because the significance of the Thailand image becomes much clearer when viewed alongside everything we already know about 3I Atlas. What we're seeing now is not an isolated anomaly, but the continuation of a pattern that has challenged astronomers from the very beginning. The antitail captured in recent images remains sharply defined, pointing inward toward the sun with a level of structure and stability that defies expectations for a comet well past perihelion. Under normal conditions, this feature should have softened and dispersed long ago. Meanwhile, two external tails, one thin and bluish, shaped by ionized gases, and the other broader and more diffuse, formed from dust particles, extend outward simultaneously. The presence of all three tail structures at once is almost unheard of in cometary literature, especially with such precision and clarity. These observational details reinforce critical questions. Why is the antitail still so strong and well structured? What type of particles are capable of maintaining such coherence? What internal mechanisms could produce such focused, stable outflows? And supporting evidence continues to build. Spectroscopic measurements previously identified carbon-bearing molecules, suggesting that Atlas may contain exotic ices uncommon in our solar system materials, capable of sublimating under lower energy conditions and releasing large particles over extended periods. Piece by piece, the picture becomes clearer. We are witnessing a comet whose behavior does not fit existing models. And that reality leads us directly into the most important question of all. This brings us to the central realization emerging from the scientific community, one that has grown louder with every new observation. 3I Atlas may force us to rewrite key assumptions about cometary physics and the behavior of interstellar objects. The configuration revealed in the Thailand image, an anti-tail that is sharper than before perihelion, paired with two distinct outward-facing tails, has created a situation where traditional explanations are no longer sufficient. Every conventional model predicts that after perihelion, tail structures should relax, weaken, and lose definition as solar heating declines and particle dispersal takes over. Yet the opposite is unfolding before our eyes. If the antitail remains stable and sharply defined, it implies that massive particles are still being released in a focused and continuous stream, long after the point where such activity should have diminished. If these are chunks of ice acting as temporary mini-nuclei, they must be significantly larger or more cohesive than expected. And if what we are seeing is the result of directed jet activity, then we are observing a level of internal organization within the nucleus that challenges long-standing theoretical assumptions about structural integrity and flow geometry inside cometary bodies. Some scientists are now suggesting that we may be dealing with a form of internal composition unlike any comet formed within our solar system. Spectroscopic readings indicating carbon-rich and nitrogen-bearing molecules hint that Atlas could originate from the extreme outer regions of a distant stellar system, formed in an environment cold enough to trap exotic volatile materials. If true, it means we are witnessing physical processes shaped by chemistry foreign to our region of space. As Harvard astrophysicist Avi Loeb noted in his recent analysis of Atlas's tail dynamics, the accumulating anomalies demand attention not because they imply something extraordinary, but because ignoring them would be scientifically irresponsible. Each new observation forces the same conclusion. The physics governing Atlas may not align with the principles we have built from studying traditional solar system comets. And that is the grand revelation hidden inside this latest discovery. 3I Atlas is not simply an unusual comet. It is a test of the limits of our understanding, an object that may permanently expand the boundaries of cometary science. Because if the anti-tail's behavior cannot be explained within existing frameworks, then the frameworks must change. The universe has presented us with an object that refuses to behave according to the rules we thought were universal. And the only question now is, what will we discover next? As we look ahead, the coming weeks will be some of the most critical in the entire observational campaign surrounding 3I Atlas. The comet is now moving steadily toward its closest approach to Earth on December 19th, a moment that will offer astronomers the best opportunity yet to measure the detailed dynamics of all three tail structures. During this window, observatories across the world, including facilities in Europe, Japan, Chile, and the United States, will be tracking Atlas nightly. High-resolution spectroscopy will attempt to determine the velocity and composition of the particles moving within each tail. If the antitail consists primarily of massive particles, it should remain stable and sharply defined. If it is formed from smaller dust, grains, or gas, it will begin to disperse rapidly. Meanwhile, the dust tail will respond to changes in solar radiation pressure, and the ion tail will fluctuate depending on variations in the solar wind. These comparative responses will allow scientists to build a dynamic map of how the comet is evolving and, more importantly, which physical mechanisms are driving its unusual behavior. Researchers will be watching closely for any structural changes such as twisting, branching, wave patterns, or sudden disruptions that could reveal whether the outflow is uniform or directionally controlled. And the stakes are high. Every new measurement has the potential to either reinforce or challenge the traditional models that have shaped comet science for decades. Whether the antitail strengthens, weakens, or transforms entirely, the outcome will reshape the conversation about interstellar objects for years to come. So, the story of 3I Atlas is far from over. In fact, the most revealing chapter may be about to unfold. As we wait for the next set of observations, one thing is clear. The universe is offering us a rare chance to witness remarkable physics in real time, and none of us know how this will end. Stay tuned.